So in this video, we're going to describe a data science concept called PCA, or Principal Component Analysis, and we're going to derive it with the help of ChatGPT. So what we're going to do is find the vectors along which the most variance in the data lies. This is important for reducing the dimensionality of our data in a linear way, which helps us perform subsequent analyses with less data, meaning less computational time and power. So recall the vector projection formula, in which you have the vector x along b. You're basically projecting A onto B, and that projection is the vector x, and the magnitude of this vector x is A dot B over the magnitude of B. And this means that if the magnitude of B is 1, then the magnitude of x is A dot B, or A transpose times B in matrix multiplication form. So say that we have data with P features and N samples, P columns and N rows. So basically, this is a set of N vectors, or N samples, in P-dimensional space. So you have P features, meaning that you have P dimensions for each vector, and you have N vectors. And you can represent that as a matrix, as shown in this diagram. So without loss of generality, we're going to assume that the data have been standardized, meaning that we have transformed it such that each sample has mean 0 and standard deviation 1. The formula is below. So we can calculate the scalar projection of these data, or we have n data points, each one being p-dimensional. So we have a vector in p-dimensional space, and we have n of them. And that vector points to a data point, or each vector points to a data point. And so we're going to project each one of them onto a unit vector called w that can point in any direction in p-dimensional space. So if we calculate the variance of these points on the w axis, then we are effectively calculating the spread of the data in that direction. So we're quantifying the degree to which the variance in our data is explained in a certain direction. So let's do it. So the variance along W is the variance of the scalar projection of our data onto W, or W transpose times X. That's equal to that summation, and remember that our mean is 0, and that's why we're subtracting 0, or not doing anything at all really. Xi is the sample vector in X. It's a column vector, but we actually take the elements across the rows in our data, X. And there you have the formula that we have for the variance along W in the green box. So let's now define the covariance matrix in terms of our data. So we have our covariance matrix represented as sigma, and X, capital X, is our data in the form of an n by p matrix, n rows, p columns, and yeah. So in summary, we have our covariance matrix, epsilon, and we have our variance along W is equal to that summation in the green. So let's combine these two facts to get the variance along W formula. Through some mathematical manipulations, you can say that the variance along W is equal to 1 over n minus 1 times W transpose XW, and you'll see that within there is the covariance matrix, epsilon. So we'll see that a bit more clearly. Right there is the covariance matrix. And so we could say that the variance along W is equal to W transpose epsilon times W. So what we're going to do is we're going to find the W that maximizes variance when the data is projected along it. So we're going to solve that constrained optimization problem in the yellow box, and we're going to say that's the maximum. We want to maximize the variance along W, or W transpose epsilon W, subject to the magnitude of W is equal to 1, because remember, we said that W was a unit vector, so its magnitude must be equal to 1. So in order to solve the optimization problem, we are going to use Lagrange multipliers. And so we're going to first form the Lagrangian function, W transpose epsilon W minus lambda times W transpose W minus 1. So in order to solve this optimization problem, we're going to take the gradient along W of the Lagrangian and set it to 0. So that means that 2 epsilon W minus 2 lambda W is equal to 0. And so that implies that epsilon W is equal to lambda W, meaning that we have a eigenvector eigenvalue problem. So we're going to have multiple solutions. And remember, we have multiple solutions because we're finding the relative maxima instead of the global maximum. The global maximum will be the maximum of the relative maxima within that eigenvector problem. So in order to find the maximum variance, we have the variance along W is W transpose epsilon W, and the set of W that maximizes the variance are the eigenvectors in epsilon W is equal to lambda W. So the maximum variance along W, therefore, is equal to W transpose times lambda W. So we're making that substitution. We're substituting in lambda W for epsilon W. And what we get there is we're going to say that's equal to lambda W transpose W. And remember that W transpose W must be equal to 1 because the magnitude of W is equal to 1. Therefore, the lambdas are the values that are the corresponding maximum variances along the W's. So in conclusion, the sets of W that maximizes the variance are the eigenvectors in epsilon W is equal to lambda W, where lambda are the sets of eigenvalues that represent the corresponding maximum variances along W. This set of W are known as the principal components. So that is the end of this video, and thank you for watching.